recording. I'm going to be talking with you about the oil and gas interoperability pilot today. This is the context for collaboration slide, which is really important to us because most of the people here at this conference are actually people who are familiar with automation and operations and maintenance related activities. Those exist inside what we call the execution environment, which is immediately behind my head, so I'll stand back just slightly further. And the actual purpose of this demo today is to start showing how we can automatically feed and hand over all the digital information in machine readable format coming from the EPC community and actually flowing through all the technologies of the major design engineering tool suppliers, bring them over, automatically hand that information over rather than doing the manual printout followed by subsequent hand jamming of data that's part of startup and commissioning these days and has been forever in this industry. And we've got to eliminate that process for qualitative as well as performance and cost reasons. This is the opportunity. They typically tell you you've got to choose 2 out of the 3 in terms of quality, time, and price. This is actually something that simultaneously improves all 3 elements in a major way, okay? So what we're really doing, again, is automating this process, then standing up an interoperable O&M environment based on all the automated process for handing over everything in a readable form. So this has been articulated down at a relatively detailed level. This will be a continuous improvement for years and years into the future, but at a detail level, we've got the interoperable O&M specifications on the right-hand side of the slide. The handover is actually occurring coming from the left-hand side of the slide where we've got the traditional EPC community working with us and with the original design engineering tool artifacts that everybody's used to. So we're dealing with P&IDs, PFDs, instrument lists, equipment list, and all the key parameters thereof. Being able to keep that in machine readable form to come over again, do handover and automated provisioning is absolutely key. All the color-coded information flows here deal with all the various standards that are responsible for the subsequent execution in the O&M environment. Many of those are standards that are part of the OpenO&M initiative. They include ISA, MIMOSA, OPC Foundation, etc. And they're all, again, properly mapped out in legend. As we go to each scenario and each use case, numbers will change. So when we get into O&M scenarios, you would see numbers over on this side. Today we're going to be focusing first on handover and second on, there we go. Second on the use case 10, which is automated provisioning. So these are not in numerical order. These are use cases that have been developed, and we really worked on the O&M interoperability first, and then we started reverse engineering our way back to saying, what do we actually now need to be digitally handed over to us in a machine-readable format so that we can do automated provisioning. Okay, we knew in advance we'd have to do the handover. We basically decided it made more sense to have the automated provisioning use case, though, as a standalone use case. So hence it's use case 10. And you'll see once again the color code moved, and there's a particular now use case and scenario for that. If we went through all the use cases for the O&M side, you'd see those numbers float all over the place over here for the various owners specified use cases. So we're building a virtual light eng unit for a plant, all right? And this was actually laid out, hand-drawn by one of our owner-operators last year to say this is a debutinizer tower, and here's how we would build it if it's a real project in a real plant. Here's what we want to do on a go-forward basis. We've agreed they'll build a debutinizer and a depropanizer. You put those two together, that becomes the heart and soul of a light eng unit in a plant, which then there are other major units in a refinery as well. But basically, this was a really good getting started point to make sure that we can do this and do it correctly end-to-end. That's a matter of scale and repetition, okay? Engineers know how to scale and repeat once we've agreed on a pattern. This is engineering, this isn't magic. So that's what we're doing with a pilot, is to make sure it's real. Magic is not scalable or repeatable, unfortunately, okay? So engineering is, all right. Now, so the suppliers that you see here today included people using technology from AVEVA, Bentley, and Intergraph, again, starting with Worley Parsons at the front end, doing the real engineering artifacts, bringing through those documents in XML format over to University of South Australia transform engine that's a semantic transform, getting them into the interoperable O&M environment, published in the O&M register in a fully interoperable fashion, then brought into IBM's advanced performance solution, which has also got integration framed in with it, the IBM IIC, and then ultimately populating an OSI soft plant data historian in full context of all the PFD and P&ID and key parameter information, okay? So we're going to walk this through end to end, and ultimately I think you'll be happy at seeing there's a real pilot going on. You can look under the covers. It's not a mock-up. It's not perfect. There's still gaps. That's the reason we're running a pilot. We have honest discussions. This is downstream. I do want to mention this month, the current month's edition, Journal of Petroleum Technology, has got a major feature piece on what we're doing in the upstream end. So there's going to be upstream pilots that go along with the downstream pilots. So SPE's DSATS team, which I'm a part of, that's their Drilling Systems Automation Technology section, will be doing this for Rig of the Future and Well of the Future, going along with what we're doing here. Caesar Association out of Norway will be handling the lead activity on the production platforms offshore. So I'm going to hand this over to Cormac and let him speak from a Worley Parsons point of view, and they are acting as our lead EPCs here, which we very much appreciate because that makes this a real activity.
Let me just, I'll introduce myself. My name is Cormac Ryan. I'm with Worley Parsons. I'm the manager for engineering data management across the Americas. I'll just preface this by saying I'm logged into my laptop, into our network, and we're going to be looking at data from an engineering perspective. This industry is looking at how can we leverage the data out of the engineering process to provide a value improvement opportunity for operations maintenance. So let me just share my screen here. And we're going to be looking at the, oops, let me just get that up there. We're going to be looking at P&IDs. Now, it's a key, P&ID is a key deliverable out of the engineering process, but a dumb drawing is going to give you little or no value from an operations maintenance perspective. So I'm going to be talking about intelligent P&IDs. So, right. So the intelligent P&ID that we're going to be system that we're going to be talking about here is Smart Plant P&ID. It's a database-driven application. It has a series of inputs, and you get a whole series of outputs. The inputs is no different from a normal P&ID. You've got a whole lot of graphics, symbology, etc. It's standards-driven. Key difference here is you've got a data capability. We've got the ability to process or put in data associated with the P&ID, the instrument data, the equipment data, the line number data, etc. This can be put in directly into the application itself, or we can actually go and use third-party apps that connect to the database and the processing. We also have a third way of getting the data in there. That's where we can export the data out of the tool, give it to the process engineers. They can fill it in like an Excel spreadsheet, and we can load it back into the system. The key point here is once you've got the data, we can now generate reports out of it, or outputs in terms of drawings. The drawing is the typical P&ID that you're normally used to seeing on a project. The difference is it has a whole series of reports that are available below it. An equipment list, a line list, an instrument list. We're going to be talking about here today and showing you is once we've got the data and we generate the reports, one of the value-added reports here is an ISO 926 XML type file. So let's go take a look at one of the P&IDs. So you saw earlier the process flow diagram. Well, here's the actual P&ID, and if we zoom into it, we're going to be taking a look in a minute. You'll see some data a little bit later on. We've got a condensate pot over here. That tag number D7 1100, you can see the nozzle numbers and the connection information in there, and we've got some more conditions against that piece of equipment for the pot, and you'll start seeing that pop up a little bit later on in the downstream systems that we're going to be looking at. Also, if we look at this information here, because it's an intelligent PNID, I can get my valve lists out of this. I can get my instrument lists out of this. I can get my equipment lists out of this. And I highlighted there's the con pot. And also, I can get my line designation table and all of the process conditions associated with this. And all of this information is transferred and available downstream. So one of the things we're going to be, whoops, let me just get past this. So one of the other slides there is, well, how do we give the value? We produce the typical deliverable. Essentially, we do is we're going to publish the information. I'm going to connect to the ISBN, and I'm then going to publish that PNID that we've just generated. I'm just going to pick it, click it, I'm going to post it, and you're going to see that pop up downstream in the systems.
Good morning. I'm Jim Klein, and we'll be switching the screens in just a second. There we go. Show my screen. All right. As Alan had mentioned, there are several different PNID vendors and other vendors participating in this exercise, just to show how interoperable we all are. AVEVA is acting as the second EPC in providing PNIDs to the pilot project, in effect acting as a project with multiple contractors would be. So there may be multiple formats of PNID, but in the end, we want all the data to end up in the proper place. So AVEVA is using as its output the Proteus format. The Proteus format was developed based on XM Plant Schema 3.3.3 several years ago as part of a FIATech project in which several PNID vendors got together to see how we could provide common output to downstream systems. And of course, it's XML based. We've been duplicating the data set that was created by Worley Parsons. And I'm going to bring up AVEVA's PNID set here. I'll be posting the fourth drawing in the series here, just so that we can get all the different PNIDs loaded into the system. And if I were to look at the properties of equipment, I would see that I have different properties that are associated with a given object. In this case, I'm looking at this drum, and we've got capacity, which is blank at the moment. We've got a design pressure and a design temperature and insulation thickness and things like that. So these are the bits of data that might appear on a PNID. In future versions of the pilot, we will be extracting data from the engineering database that would have 50 or 60 attributes that are pertinent to the downstream systems. In this particular pilot, we are limiting it to just a few bits of data. So once I've decided that I'm finished with the drawing, I can go into the data management aspect of it. And I have several choices. One, I can just issue an ordinary or a plain ISO 15926 output that can be used in any number of ways. And I would point out that this same type of interface is what allows the output from Worley Parsons smart plant PNID to be compared to an AVEVA PDMS model. So there's interoperability in that system in that way. So different contractors use different tools for different parts. This allows that comparison that's so important for the integrity and checking of the data. So I'll just push the button for MIMOSA server, and just like the Worley Parsons group, it's going out to the IBM cloud and will eventually end up in the hands of my colleague here, who will be demonstrating some of the transforms that are going on.
Thank you, Jim. Hi, my name is Georg Grossmann from the University of South Australia. Okay, I'm switching over to the screen. Can you see that? Okay, the task of the University of South Australia in this handover demonstration is the building of the transform engine. So the transform engine is the bridge between the 3 different suppliers and the register. And before I go into more detail of the transform engine, I wanted to explain you a little bit more about the Bentley part, because unfortunately nobody from Bentley could join today. So what Bentley provided us is the same information as Intergraph and AVEVA provided us, but in a different format. This format consists of 2 files. The first is an OWL syntax, and the second one is an ECXML syntax. And these 2 parts contain different information. So in the OWL file, you have information about the items, the identifiers, the properties, the equipment types, and the breakdown structure. And in the ECXML message, there's information about the topology, the piping connections, flow direction, and the geometry information. And this information is passed on to the UniSA 5926 transform engine. So what the transform engine is doing is it consumes the information from all 3 suppliers on an ISBM server channel. And internally, it imports the different formats. So this is XMPlant format from Intergraph, the Proteus format from AVEVA, and the OWL and ECXML format from Bentley, and then lifts this information, which is X, to a conceptual level. And we do it that way because on that level we can more easily check that the semantic transformation is correct from the ISO 5926 to the MIMOSA side. When we have done the transformation, we export this down to XML, to CCOM XML, and post this then on the ISBM channel again. Now for demonstration purposes, we developed a web interface, so you can see what's going on the ISBM server. And what you can see here is the interface, which is in a standard web browser, where we have the information about the ISBM server and the channel we have subscribed to. And then down below, you can see the different messages that we have received. So here, for example, we have received the Bentley message. This is something that I have posted previously. And here is the AVEVA message and the Intergraph message. And on the right-hand side, you can see the message IDs of the output of the transformation. So we have 3 transformations for all 3 suppliers. We can hand over now to Ken.
My name is Ken Bever. I work with a company called Assetricity. Our company is been involved with trying to make the standards to be able to utilize those standards effectively, including the ISO 15926 and MIMOSA standards. As you can see on this diagram, we've taken now from Georg the information that's been transformed into MIMOSA XML format called MIMOSA CCOM ML. This is a standard for operations and maintenance systems, so that such as our maintenance systems, our tag management systems, our PI historians or historian systems can consume information in a way that makes more sense to them instead of sending them an entire engineering P&ID diagram, which is like, wow, this is really too much. We don't need all that. We need to be able to just get the tag information that we really care about and all the attributes about the tags so we can populate and set up our historians, our operational systems, our DCS, our main systems, et cetera, in the plant. So we've now just got the data we need to now be able to take and provision other systems. One thing this system does, this register system, is it figures out what system did this come from? What's the system of record for this particular piece of information? So I know that I need to go back to that system if there's updates to get those updates. So it manages systems of record and where they came from for every piece of data that we receive in. It also keeps track of taxonomy registrations. You heard 3 terms being used for this same object today. When Cormac started off, he called it a pot. I believe when Jim talked about it, he called it a tank, or I believe it was, or drum. So you've heard tank, drum, and pressure vessel, and we could actually have a horizontal vessel. The problem we have with our English language is we have synonyms for the same object, but we need to really classify it in the same way. That's the value of the ISO 15926 standard. It's an ontology that lets us be very specific about what this object is. Let me just show you, because what we've taken is the taxonomy information, and this has been now in a 15926 format. Here's all the different devices, but the nice thing is that it actually ties us back to a website called the Reference Data Library, the RDL. Let's see if we can show it up here. My screen is kind of slow refreshing. Let me just. Can you see it? Oh, here you go, finally. So you see that we've got the information that was, we received all of these different equipment types, equipment classification types. One of them came across from 15926 that's a vessel. Okay, now that, again, was called maybe different things in different systems, but the one thing we all want to check on is this. Whoops, sorry about that. Stop, fell down. Right here where it says the RDL, and it gives a specific number and a pointer, a URL pointer to us. So when we click on that, it actually takes us, and you could do this because it's available now anywhere that you can access the web. You can access that and actually bring up the definition of that in a reference data. This is all tied back to the ontology. So we know that this is a container, it's a fluid container, it ties us all the way back to a particular type of thing. You want to hit that? And so that's a specialization of that. So that's why this is more than just sending just text around. This has actually got an ontology-based representation of the information, which I think is key for us to have interoperability, so we know what we're talking about. The system, not just humans, but our system, what it is. So when we go back here, we've now imported the data that came across, transformed, and one of those objects we received was this D1100, the horizontal vector. And guess what? That is the type. The type ties back to that taxonomy we just saw. It tells horizontal. We have details. We have a globally unique ID now for that object across all our operations and maintenance systems. So everyone uses that as a common interoperability identifier, so everything gets linked to the same object. Instead of being, you call it 1, 2, 3, I call it 4, 5, 6, and we don't have any kind of activity. So once we have that tied together, we also want to keep track of the system of record. In this case, it tells us that this came from Intergraph Smart P&ID It's on the engineering data sheet, and they're the system of record for this piece of data. Now, we could have another system, a maintenance system will have additional data sheets, or my DCS or my historian may add additional properties, but we know what system that came from, and we can tie it all together this way. Now, we can look at all that. If it looks good and we now are ready to provision a system, we're going to provision the IBM system that's waiting for this information. It's called IIC, and it wants to be able to do the kinds of things that will need to be done for operations and maintenance, and being able to tie together and look at monitoring and setting up historians and provisioning other systems. So I'm going to go ahead. I've received this message. I'm now going to publish. I'm going to set up a publication on this channel. Again, this ISBM allows everyone to can publish or can consume information. I can be a publisher or a consumer. In this case, I'm now going to publish onto the ISBM, and I'm going to give it the debutinizer, and I'm going to say post, and off it goes. And I'll turn it over to our IBM.
I'm Bruce Hyre from IBM, and I'll be picking up what Ken just sent, if I can get this clipped. Okay, so let me share my screen. Now our focus is on integration and analytics. So we want to integrate the data based on an extensible semantic model that's based on open standards. That gives you access to the descriptive data as well as the live data. And by providing that integrated data, now you can build analytics based on all that federated data. So here's our model. We're too far to the side. Okay, I'll hold it here. Okay, so we're going to pick up the data coming downstream from the register from Assetricity. And let me switch here to a little diagram that will show you the context. So over here we have IBM's implementation of the ISBM, which is the bus that all of the partners have been exchanging data on. This is out on the IBM cloud, available on the public internet. This is where it's all been exchanged. And then you can see here, essentially you'll see here, here's our ISBM. Partners exchanging information. We'll be picking this up into IBM's EDH engineering data handover technology based on our integrated information core, IIC. And here we have the core of IIC is a reference semantic model based on the open standards, OWL RDF, ISA 95, 98. All these are incorporated into our system, and it's extensible for additional models as they evolve over time. So we have an adapter picking up that CCOM that's been passed to us. We're going to provision it in the model, and I'll show you the transactions where that happened in the ontologies. And then we'll flow that down to Pi. And to focus on the pieces you'll be seeing today, we're going to flow it to Pi and provision tags, the live Pi stir. And then we'll go and subscribe to data there and get live data out of the OSI Pi server, all driven through this core semantic model, describing where things are and what they are. And this provides us a central integration point where we can talk to Maximo and provision equipment in Maximo or any other systems. It's a pluggable architecture to allow us to bring in new standards and new products that we can integrate with. So we'll be talking OPC, DA. We support all the various standards there, as well as talking CCOM over the ISBM. So let me go to the live system, and I'll show you an ID that we picked up over the ISBM, the RSM tree, the model tree as was provisioned from the downstream, the data coming downstream, and then the tags provisioned. So here's a quick snapshot of what the RSM tree would look like. This is all configurable, how you organize and categorize. And when I jump over to our live system, just to show you it's real, we've loaded the ontology into our model server, Here's the model server itself, and there's the reference semantic model, the standard RSM. We got transactions from upstream systems, loading all the different portions, and then these are the actual graphs within the RSM. So now if I switch over to my other UI, here are all the diagrams that have come across. Okay, so it takes just a minute to load because I'm pulling this over the Wi-Fi system here from the public internet net cloud server. So if everybody would stop using their machine so I can have some bandwidth here. There it goes. Okay, and there's our debutinizer. Okay, that's real live data. I could point you to this. If you type that URL into your system, you would see the same thing. Okay, and just because of the speed, I'll only show you one more here. Okay, that's going a little faster. And there's the condenser. Okay, now the model itself, you'll see the RSM tree here. There's our debutinizer, and we'll see all the tags that came across as well. So let me switch over to, I lost my Pi server. Let me go connect back to Pi. Okay, here's OSI Pi. Let's go look at the tags that were provisioned, again, from that same data set. So for any of you who know that Pi, this is really how it looks, okay? And there's all our tags. And we have 1,292 tags that came all the way downstream, okay? So those have been provisioned. Now, what's nice about Pi, you can add one little attribute that says simulate the value because we don't have a real debutinizer on our IBM campus. I lobbied for one. My boss said we didn't have the funds, so maybe next year's budget. Okay, so whoops. Now I'll go back here, and I'll show you we're actually getting live data on this same UI. In this case, I picked this tag. I think everybody else mentioning that tag. Oh, the values just changed there. If you notice that. Here, 3 of the measurement values associated with that tag. If we give it just a couple of seconds, you should see the values actually change on all 3. Or actually, we have more. And there they go. Okay, so that's live data. We got the CCOM from the upstream systems. We provisioned it in our RSM model. We talked to Pi, provisioned all the tags in Pi, and we've subscribed to them. Now on the north side, IEC provides federation of all this data so that you can have multiple systems, multiple Pi servers or any vendors back there, web services, database. You can pull all this data together into one place to do your analytics. So what I'd like to show you now on the north side of that diagram I showed you, we're going to connect to the IBM IIC using standard OPC. So here's a Matricon OPC browser. And there you see the IBM IIC OPC proxy server. We're already connected, but I'll add a tag to it. If Windows, thanks Bill Gates. Okay. And once again, you'll see RSM representation of all this data. Here's our structure, enterprise refinery, area A, in the light ends area. There's our debutinizer, and there are all our tags. So I can, let me find a tag that looks familiar. I thought I saw it there. Oh, there's the 1100. So let's go ahead and subscribe to that measurement value. And we have a value, and if we watch that, we'll see it update. And surprisingly, it's the same value that you would get straight from Pi down on the south end. So again, standards-based data coming in, into a standard RSM model, provisioned in Pi, flowing data up through that central integration hub so that you can do your analytics all from one place. Okay, so now back to Alan.
So first of all, I'd like to thank all of our participating suppliers. This is real work. This is not salespeople, okay? So you've got real core product development teams sitting here. So those of you who are interested in asking questions, please do so. Very different from what you'll typically see at the average booth at the average trade show, all right? Real work being led by a real EPC, like we're building a real area of a plant. We're intentionally got the real engineers, the real development people, so they can be asking questions of each other, putting this under continuous improvement. That's a key differentiator. All right. The other thing I want to emphasize is because of the standards component of this. You know, sometimes we say integration and people go, yeah, we've been able to do integration for 25 or 30 years. That's true. Okay. But the way this has been done, okay, it's using IBM's IIT, which has the label of Information Integration Core. There's a lot of extensive built-in integration capability there. When they added the standards-based enablers to it, this suddenly turns it into an interoperability enabler. And that's a key differentiator and value in our operator community, all right, because this gets down to a sustainability topic now as well, okay? And in that sense, it's very easy in a relatively small system to integrate one time through. The larger that system gets, the harder it is to do, and then when you get a system of systems, it becomes increasingly difficult to do, okay? And I've seen in the case of a U.S. government effort in one military service branch, $1.8 billion spent on such an effort, which was then basically put away, okay? Because it was impossible to get it end-to-end integrated before the front end started breaking again, all right? Now, interoperability is different, so it is about sustainability. So when you do standards-based interoperability, yes, the underlying technology is what we've used for integration for years. IIC is a good tool for that, okay? Standards-based interoperability actually means that now the individual suppliers have standards they can look at. They can all build commercial off-the-shelf adapters that support sustainable interoperability, and that really helps us then when you got really complex systems, and I'm not going to call out any particular folks by any name here, but you can just imagine recent incidents over the course of the last few years that you might have heard of, and then somebody makes the infamous statements, well, I don't know about it, or I didn't know about it, therefore I couldn't do anything about it, okay? Sadly, this is all too often the real case, and one of the issues is you can have point-to-point integration of all these complex systems, but it breaks down. And when it breaks down, guess what? That's not always the highest priority to come back and get fixed because everybody has got their, quote, real job to do, unquote. And therefore, what you wind up discovering is eventually enough of these links break down, information does not get passed from the left hand to the right hand on up to the head, and then an incident occurs. And sometimes it's a tragic incident. So this is a key thing about how do we have sustainable systems for a sustainable planet. And they actually fit together. Okay, so again, sustainable interoperability, I believe, is a key differentiator, and the way to get there is standards-based interoperability platforms, which is better for everybody. So thank you very much for coming, and again, thank our students again for participating in this, if you would.